today's video, so we're recording, yep. Today's video is on change of state, and all that is really is that materials have three states, and we'll just consider liquid, solid, and a gas. So if you think of water, water has three stages, or three states. It has water, liquid, solid is ice, and gas then is the vapor or the steam. So depending on the temperature, it'll go through different phases. You'd have touched on this in materials as well. So we all know that material is a liquid above 0 degrees C, it's a solid below that, and it's a water above 100 degrees C on Earth at our level. Obviously it changes as you go up. Swig of tea, hang on. As you go up, change in pressure, things change a bit. We also know that mercury is a liquid at room temperature. So, not all metals are liquid at room temperature. So we can change the state of a material by adding energy in the form of heat, which will change its temperature. So by adding heat or adding energy to ice, we can change the state to liquid. And if we keep adding energy, we can change the state from a liquid to a gas. That's when you boil your kettle. So if you add energy, heat, to ice, it will change state to liquid. The bonds are being broken down and it's going from a solid, ice, into a liquid, which is water. Continue to add energy to the water and it will change to a gas. So the same thing happens for oil. If anybody from Valero is listening to this, that's why we boil oil, because things happen when we boil oil, things come off it. Alright? Oh, it's nice tea, this is. So we can change the state by adding heat. So we get a graph like this, look, a change of state, or a phase diagram, some people call it. And all it is temperature here, and the amount of energy we're adding. Don't forget, temperature is just energy, really. So you could say it starts off here. This could be one phase, which is a solid. We'll use ice. So at a certain temperature, ice or water will be in solid form. So this is meant to be the energy. So as we're adding energy, the temperature goes up. So up comes the temperature, up comes the temperature, more energy, more energy, more energy, up comes the temperature. Gets to a certain point, which we'll call 0 degrees, which is the melting point. So at that point, this ice now is starting to change state to water. But it doesn't go straight away because you have this thing here, you have this straight line. We're continuing to add energy and add heat, but nothing's happening to the temperature. Now this bit is called the latent heat. Latent section is a straight line. And what's happening there is all the energy that we're adding is being used to break the bonds. Not being used to raise the temperature, it's being used to break the bonds. It's breaking the bonds from solid into liquid. In this case, it's breaking the bonds, ice bonds, into water. So all the energy is being used to break the bonds. So it changed from a solid into a liquid. So this bit here is half and half. It's like a bit of a mushy state. So as you're going along here, when you get to this point, all the bonds are broken and it's fully melted. So now, at this point, it's fully melted. So all the energy has broken these bonds and now it's all liquid. In our case, it's all water. So now, the energy is being used to break the bond. So now the energy is being used to raise the temperature. Up comes the temperature. Up, 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 up. More energy, more energy, more energy. Temperature rises, gets to a point. So this is all liquid now, or water, or mercury, or liquid iron, or whatever. Gets to a point, right, where it now starts to change state again. So now we're going to go from water, we go from a liquid into a gas. So water into steam. We know this point for water 100 degrees on Earth at ground level. So at 100 it starts to evaporate, and you will see the evaporation happening. Again, you have this latent heat of evaporation because the bonds are being broken down. The bonds are being broken from liquid to a gas. That's why when you boil your kettle, you will see steam coming off because the bonds are breaking and there's some gas coming off. So what's happening here is it's going water and then it's gas and steam, whatever. So it's a bit of gas and a bit of liquid. So we're at this stage here now, the gas stage. Gets to this point and it's all there's no water left. It's all converted into gas. And then if you keep increasing the energy, the gas expands and we've gone into steam or vapor. So depending on how much energy you add or heat you add, you have different phases. And all materials will do this type of thing. Right, it'll go up, have its latent heat, up again, latent heat of evaporization. So we can work out how much energy we need to put in to go from ice at this temperature to water at this temperature. Same thing if we had aluminium, gold, oil for labour boys, how much energy we need to put in to get oil up to a certain temperature so we get the certain hydrocarbons of it. More tea. Phase diagram. So the increase in energy breaks the bonds of the material. Solid turns to liquid, liquid turns to gas. The latent sections, which are these bits here, look, are where all the energy is being used to break the material bonds. So this is latent heat of evaporization. Latent just means hidden, hidden heat. Latent means hidden, hidden heat. So the latent sections are where all the energy is being used to break the bonds. Once the bonds are broken, the temperature starts to rise again. So once all the bonds are breaking, it's gone from solid, now it's a liquid, fully liquid here. So up we go again. Fully gas here, up we go again. Nice and easy. So we can work out, like, if we want to work out the energy we need to heat up a bit of ice from -53, say, all the way up to water at 50 degrees C, how much energy do we need to input to get that change of state? Or if we want to change ice from -53 up to 100, so if you want to boil it, how much energy have we got to put in? So as normal, there's a formula. Here's a formula. So delta U just means change in energy, how much energy we need to put in joules. M is just the mass, so the mass of water, the mass of gas, mass of aluminium, the mass of gold, the mass of oil, mass of lead. This thing called C is a constant. It's a specific heat capacity. Obviously, some metals melt quicker than others. Right, so that is the how much temperature you need to change per kilogram of material. So that's a constant. So obviously aluminium will have a different one. Water will have a different one. Gold will have a different one. It's how much heat capacity of the material is. So that'll just be a number. You'll have that number. Delta T just means change in temperature. It's a change, so it can be in degrees C or degrees Kelvin. It makes a difference because it's a change. So this will give us how much energy we need to convert a certain mass of something from one temperature to another. So here's an example. Change color. Let's go to green because we're on copper. So calculate the energy needed, which is this now, to heat up 2 kilograms of copper from 100 degrees C to 250 degrees C, both in the same units, so nice and easy. Now, the specific heat capacity for copper is 386 joules per kilogram Kelvin. That's the number we're going to be using. Don't forget, it's the difference. So if that was in Kelvin, it'll still be the same difference, won't it? So it just makes no difference. So here's our graph. So we know that copper at 100 degrees C is solid, say. So 250. So we need to work out how much energy we need to put in to go from there to there. It's not going to melt it. So the change in energy is going to be the mass, which we know is 2. The heat capacity is 386. And the change in temperature is 250 take away 100. So that's what's in there. 250 take away 100. So there's your mass, 2 kilograms, 2 kilograms. Specific heat capacity is 386 for copper, just 386. Look, there's no killer there. The change in temperature is 250 to 100. It's from there to there, look. It's coming up the slope. So put that in your calculator. 2 times by 386 times by, you shouldn't have to do that on a calculator, but we'll do it anyway. This will give us how much joules we need to put in to change that copper from that 100 to 250. 11,500 joules per CNG. Thank you very much. That's how much kilojoules, that's how much energy we need to put into the copper to change its state from 100 to 250. We're not changing the state, sorry, we're going from 100 degrees to 250. That's how much joules. Now later on in the video we're going to talk about power, because power will tell us in how much time. So this is just how much energy we need to put in. So there's no time involved yet, because it'd be quite hard to change copper from that temperature to that temperature in a second. But that's coming. So that's how much energy we need to put into copper to go from 100 to 250. It's always handy to draw the graph so you know where you are. You haven't got to draw the graph, but it makes a bit of sense sometimes. Now, like we said, this is when the bonds are broken, right? So that when we get a flat section here, we get a thing called latent heat. So we get different values. So this would be latent heat of fusion. So when we're going from solid to liquid, we'll have a thing called latent heat of fusion, which would be like that UI. And the same thing will happen when we go to evaporization. We'll have latent heat of evaporization. So when we're in like a normal state, we'll have a C value, but when we've got this latent heat, we'll have a different type of thing. So when a material is changing latent section from solid to a liquid or a liquid to a gas, we don't use specific heat capacity. We use latent heat of fusion and latent heat of evaporization. So that there is how much energy, that's your mass again, and that's your value. It's a constant. So it's another constant. It's a constant value. Constant, right? Constant. Can't write with my mouse. Constant. So in this example here, we need to work out the energy required to completely melt. Don't forget, it starts to, so this is ice, this is naught, so it starts to melt. The bonds have been broken, it's starting to melt. At this point, we assume it's all water. All the bonds are broken. It's all water, so it's completely melted. And then we can go on to heat the water up. So calculate the energy required to completely melt, so which means we've got to be here, ice of mass 5 kilograms into water. So we've got 5 kilograms of ice here. We want to completely melt it. Don't forget, the energy has been used to break the bonds. So it's going from a mixture of ice and water like a slush puppy until it gets to here where it's all water. The temperature is not moving until we get to here because the energy has been used to break this down. So to find that energy, that straight line there, we need to use this. We know the mass, it's 5, and the latent heat of fusion, this UI thing, is 334 kilojoules per kilogram. Don't forget the killer. So that will tell us how much energy we need to go from there to there. So we can work out from there to there, one stage, and then we can go from there to there. So when we're using the C value, we're going up the hills, up the hill. When we're coming across the straight line, we'll use the U values. So to heat up 5 kilograms of ice, not to heat it up, sorry, to change it completely from ice into water, M times UI, we know the mass is 5, and we know the latent heat of fusion is 334 kilojoules. Another cup of tea. So don't forget the killer. So we'll do 334 times 10 to the 3 times by 5. 167 minus a couple of noughts. Do that if you want to. So 1.6 megajoules. Quite a lot, really. So to go from that point where it's completely frozen to completely melted into water, basically, we need that much energy. So 5 kilograms of water. It take that much energy to heat it up, or melt it, sorry, completely melt it, because we're not heating anything. The energy is being used to break the bonds. So when we're going up the hill, I guess we'll use the C value. When we're going across here, we'll use the U value. So now then, I guess a bit tricky now. So we've got another example. Let's change color. So calculate the heat energy. So it's going to be that again. To convert 2 kilograms, that's your mass, of ice at -10 to water at 45 degrees. So we've got 2 kilograms of ice at -10. We want to heat it all the way up to melt it, and then heat the water up to 45 degrees C. How much energy do we need to do that? The specific heat capacity of ice, that's the C value. C value is 2.14 kilojoules. The specific heat capacity of water, that's the C value for water, is 4.2 kilo. And the latent heat of fusion of water, which is going to be that U value, is 334 kilo. So the C value for ice is 2.14 kilo. The C value for water is 4.2. And the latent heat of fusion is 334 kilo. So that's the formula we're going to be using, that one and this one. Now this is where it is handy to do a little graph. So we know that this is what it's going to look like roughly. We've got ice at -10, so I would draw a graph. I'm going to scale it, so -10 is down here somewhere. Obviously we're going to add the heat, and it's going to get to a point where it's starting to melt. And then we're going to keep adding energy. It's going to convert from ice into water, completely melted at that point. And then it's going to heat the water up to 45. So we've got to work out the energy to go, section 1. So from up the hill to there. So from -10 to 0. So we'll use this formula here. Then we've got to go from there all the way across to here. So we'll use this formula, because there's no change in temperature, it's just the breaking the bonds bit. So that will be part 2. And once we get here, we've got to go up the hill, so we've got to go from 0 up to 45. So we'll use that formula there again, because we've got a change in temperature again. And we've got a C value for water, which is there, and a C value for ice, which is there. And that U value will be here. So you're going to have 1, 2, 3 things. So first one, to change ice from -10 to 0. -10 up to 0. We've got to use this formula. That's why it's handy to draw a graph, because some people they'll try and just go straight from there to there. And they'll forget to do this bit. They'll just, right, so you need to go 1, 2, 3 bits. So part 1 is going to be MC, change in temperature. We know the mass, assuming the mass doesn't change, 2 kilograms. minus 10 up to 0. And the C value for ice is 2.14 kilo. There, look. So 2.14 kilo, and the change in temperature is going to be 0. Take away minus 10. Let's go from minus 10 to 0. It's warming up. So the change is 10. So that'll give us the energy. That'll give us the energy to go from there to there. Calculator. 2 times by 2.143 times by 10. 4 to 800. 4 to 800. Which means that we've got to go from there to here. We need to put in 4 to 800 joules of energy just to go from there to there. Now we've got to this point now, 0 degrees. We need to work out how much energy to go from here all the way to here. So we've got to melt the water now completely. So we'll use this. Completely melt ice into water. This is what we're going to be using, the latent heat bit, which is this bit here. There's no increase in temperature, just the energy is being used to break the bonds. That's 0 degrees and that's 0 degrees. So it's ice there, and it's starting to go mushy. It's all water there, so we need to work out how much energy we need to go from here to here. So M is the same, and the latent heat of fusion of water is 334. Latent heat of fusion of water, 334 kilo. So M times U. So there's the M and there's the U. So 2 times by 334. 334. You could put that in if you want to. 66. I've done that. So 668 kilojoules. Which means to go from here minus 10 to 0, we need 42800 joules, and to go from 0 to completely melt this water, for section 2 we need 668 kilo. So now we know how much energy we need to get to this point. It's going to be that plus that. But now we need to work out how much energy we need to get from 0. So the water now is at 0 degrees C. How much energy we need to heat this water up all the way to 45 degrees C. This formula here again. Because now we've got water, we'll assume the same mass, and we've got a change in temperature now, which is going to be 45, because we've got 45 and 0. The latent heat, so the specific heat capacity of water, because now it's within this water section, is 4.2 kilo. So section 3, 0 to 45, same formula. There's your mass, there's your C value, change in temperature. So C is 4.2 kilo. Yeah. The mass is 2, and the change in temperature is, down here. Change in temperature is 45 minus 0, so it's 45. So put that in your calculator. So it's 2 times by 4.23 times by 45. 37800. You could do that if you want to. So that's how much energy we need to heat the water from 0 up to 45, 37800. So from there to there, section 3, we need 378 kilojoules. So we've worked out from there to there, 428, all the way from here to here, 668, and all the way up this hill, 378. So the total is going to be that plus, total is going to be this plus this plus this. So we know we have a better diagram to go from there to there, 42800, to go from there to there, 668 kilo, and from there to there, 378,000. So to get water, to get ice from -10 all the way up to 45 degrees water, we need this plus this plus this. So all of that added up will give you that amount of energy. That's how much 1 megajoule we need to go from -10 ice all the way up to 45 degrees water. Let's just check that on the calculator. 668 plus 42800 plus 378123. Thank you very much. Right, either leave it like that or press E and G. That's the energy we need to go from -10 ice up to 45 degrees water. Change in state. There's no time involved yet, so we don't have any power yet, but that will come. And here it is. So, heat exchanger. We need to convert 5 kilograms of water at 50 degrees C, more tea please, into steam at 100 degrees C in 4 seconds. The energy required to convert the water into steam is 11.5 megajoules. If the input power is 29 megawatts, calculate the thermal efficiency. Now, this one, so we know we've got 5 kilograms of water. So I'll just draw a little graph. So, because we haven't got to work out this energy because we're given it. So we've got 5 kilograms of water at 50 degrees C. So we'll say it's here. So this is water now, right? So it's water, H2O, at 50 degrees C, which is by there. So into steam at 100. So here. So here's the water. It's going to go up and start to evaporate. So the steam, that's going to be 100 there, isn't it? Because it's going to start to boil. Completely into steam is there. 100 here. So that's steam. So it's telling us that the energy needed to go from there all the way to there is 11.5 mega. So we haven't got to work that out. I mean, you could have. You may have to do an assignment. So we know to go from 50 degrees there to 100 degrees. So to get basically 5 kilograms of water from 50 degrees to boiling, all steam, water's gone, it's all steam, we need 11.5 megajoules of energy. It's doing that in 4 seconds, which is quite a lot. For 4 seconds anyway. So you may have worked that out using this method, that and that and that. So it'll give you the energy. So if the input power is 29 megawatts, calculate the thermal efficiency. Now, we're saying we're pumping in 29 megawatts into this heat exchanger. And it's using that energy to convert. We need to work out its efficiency. All right? So power is worked over time, which we should know. So now we've got work done, which is energy, which is this. And we've got time, which is seconds. You may also know efficiency is power out over power in. Times by 100 to get efficiency as well. So the efficiency of something is the power out over the power in. So we need to work out, so megawatts is power. So we know the power in, right, is 29 megawatts. It's pumping in that amount of power. Now, is it using all of that? Or is it using half of that? Or is it using whatever? I'll tell you there, look, that's the answer. So, we know that the power in is 29 megawatts. So what's the power out? So the power required to convert. So the power required to convert is work done over time. We know the work done. It's 11.5 megajoules. There, look, 11.5 mega. Time, 4 seconds. So to put that amount of energy in 4 seconds, we need that amount of power. Because power is work done over time. Work done is how much we've calculated or we've been given in this case, which is that. Divide that by 4. There we look. 2.875 megawatts. So that's how much power we would need to turn 50 degrees of water into steam at 100 in 4 seconds. How much power. That's how much energy we need. We need 11.5 megajoules of energy. And to get that energy, we need that amount of power to do it in 4 seconds. So the power out is 2.875 megawatts. So the efficiency of this exchanger is power out over power in times by 100%. So the power out is 2.875 mega, because we just worked it out, and the power in is 29 input power. Times by 100 to get as a percentage. So we can do it like this if you want to. So we'll do 2.875. You can put the 6 in, but because they cancel out, but we'll do it anyway. 29 to the 6 come there. Times all of that by 100. 9.91% efficient. So this thing, heat exchanger, is 9.10%, 10% efficient, 9.91% efficient. So that's just working out efficiencies of boilers and things like that. So you work out how much energy you need to convert water or oil or aluminium to a certain state. Right? In this case, we've been given the number. In this question, we had to work it out. So for example, this one, I'll just finish off here first. So power is worked on over time and efficiency is power out, power in. So we know how much power we need to do this. And then divided by the power out. Power out over power in gives us the efficiency. So this one here, so we know that to go from minus 10 up to 45 degrees, so ice at minus 10 up to water at 45, we need that amount of energy. So say if we wanted to do that, say, I don't know, in 25 seconds, say that was the process, you need to convert ice at minus 10 up to water at 45 degrees in 25 seconds. How much power do we need? Right, so we could do power is work done, which we know, which is this, 1 mega all over time. So we know the work done is 1 times 10 to the 6, say. I'll just round that up. That's the work done. Energy joules, look, divided by time, which is 25 in this case. So if you wanted to pick a motor or something, how much power do we need this thing to work at? We'll do 1 to the 6, that's the work done, divided by the time. So we're saying 25 seconds to convert that completely. So 40 kilowatts of power we need to put in. That's change of state. So it's changing it from a solid to a liquid to a gas. So we need two formula. There's that formula there, look, and this formula here. Alright, it will be an assignment question, that formula there, look, and this formula here. When you're going up the hill, you use this formula. When you're going across, right, the land the land. When you're going across here, you'll use this formula. So just working out how much energy we need to convert a material from one state to another. Don't forget, it may help you to draw the graph so you don't miss sections out. And then this bit is working out how much power and what's the efficiency of things. Hopefully that will help you a bit. There will be an assignment question on this, and there will be questions on Moodle for you to do. But for now, over and out.